Hi students, first of all I welcome you all to my fourth video on the chapter surface chemistry. In third video we discussed different concepts of catalysis, is it not? At the same time we started the discussion on enzyme catalysis, wherein we discussed the characteristic properties of enzyme catalysis, examples for the enzyme catalysis, is it not? Now at this moment in the fourth video we are going to continue that particular discussion, enzyme catalysis, with the mechanism of enzyme catalysis. That is, I can make use of this mechanism of enzyme catalysis in order to understand how exactly enzymes will accelerate rate of biochemical reactions. For that purpose, I can make use of lock and key model. This is one of the models available for understanding mechanism of enzyme catalysis. Apart from this model, we have one more model, what we call it as induced fit model. But as far as your NCERT textbook is concerned, we are supposed to discuss only lock and key model of, yes, it is the enzyme catalysis. Look at this. As far as enzymes are concerned, enzymes are characterized by various cavities and pores on their surfaces. These cavities are characterized by definite shape possessing certain active functional groups. These cavities are characterized by definite shape possessing certain active functional groups like OH group, NH2 group, COOH group, and of course SH group. These are the active functional groups that you will find in the cavities of the enzymes. These cavities with active functional groups, they are called as active centers. Totally, the surface of enzyme is characterized by active centers. During enzyme catalysis, the reacting molecule known as substrate with complementary shape fits into the cavities of enzyme to form enzyme substrate activated complex due to its reaction with active functional groups in the cavities of enzyme. That is, during enzyme catalysis, the reacting molecule known as substrate with complementary shape fits into the cavities of enzyme to form, yes, it is enzyme substrate activated complex due to its reaction with active functional groups in the cavities of enzyme. And this enzyme substrate activated complex is unstable, that decompose to form what we call it as products. So this is what we call it as the mechanism of enzyme catalysis. And of course, I can represent this mechanism of enzyme catalysis by using this particular, yes, it is schematic diagram. Look at this. This is enzyme characterized by cavities with a particular shape. This is enzyme characterized by cavities with a, yes, it is a definite shape. These cavities are characterized by active functional groups. And this is substrate molecule. Look at the shape of the substrate molecule. The shape of the substrate molecule is complementary to the shape of the cavities of the enzyme. Such type of substrate molecule fits into the cavities of enzyme by its reaction with active functional groups to form enzyme substrate activated complex that I represent like this. And this particular activated complex decomposes to form products along with the regeneration of enzyme that is being used in biochemical reaction. So this is what we call it as the mechanism of enzyme catalysis. And of course, as far as the enzyme catalysis is concerned, enzyme catalysis is highly specific. That specific nature of enzyme catalysis can be, yes, it is explained by making use of this lock and key model. Look at this. Here, the substrate can form activated complex with enzyme only when its shape is complementary to the shape of the cavities of enzyme. Otherwise, enzyme substrate activated complex will not be produced. Because of that, only a particular reacting molecule with complementary shape can form, yes, it is activated complex with, yes, it is enzyme. Otherwise, a chemical reaction doesn't take place. Because of that, enzyme catalysis is highly specific. Just observe, I am using a term lock and key model here because look at this, a substrate molecule with complementary shape fits into the cavities of enzyme, just like particular key fits into a particular lock only. That is, if the shape of the key is complementary to the shape of the cavity in the lock, then only that key will fit into the lock. Like that, a molecule with complementary shape can fit into the cavities of enzyme to form activated complex. This activated complex decomposes to form products. And this is what we call it as, yes, it is mechanism of enzyme catalysis. And of course, The whole mechanism of enzyme catalysis can be summarized in 2 steps. Let us see one by one. In the first step, that is the first step is formation of enzyme substrate activated complex. This is the first step, formation of enzyme substrate activated complex. So that I can represent like this. E is the enzyme that interacts with the substrate molecule. As I said, the shape of the substrate molecule is complementary to the shape of the cavities of enzyme, and that results in the formation of enzyme substrate activated complex. ES star I can represent. Okay, now ES star is it is enzyme substrate activated complex. And in the second step, there is a decomposition of yes, it is enzyme substrate activated complex. Yes, decomposition of enzyme substrate activated complex. This is what we call as the second step, decomposition of enzyme substrate activated complex. That is ES star, yes, is decomposed to form, yes, it is products, along with the, yes, it is regeneration of enzyme here. So these are the 2 steps involved in the mechanism of enzyme catalysis, and that is what we call it as enzyme catalysis. Now at this moment, we'll go to the next topic in the chapter surface chemistry, that will be colloids. We'll see that, yes. So let us see one more topic, that is what we call it as colloids under surface chemistry, right? Before discussing this, colloids, let me give you some basic information as far as the concept colloids is concerned. Mixtures are classified into 2 types. It will be homogeneous mixtures. Another is heterogeneous mixtures. So this particular aspect you studied in the chapter solutions. That is, mixtures can be classified into homogeneous mixtures and heterogeneous mixtures. As far as homogeneous mixture is concerned, these are the mixtures in which the composition of the mixture is same throughout the mixture. That is called as homogeneous mixture. Whereas in the case of heterogeneous mixtures, the composition of mixture will not be same throughout the mixture. So that is what we call it as homogeneous and heterogeneous. And as far as homogeneous mixture is concerned, I'll give one example, that is a sugar solution, or you can say solution of sodium chloride. A sugar solution is an example for homogeneous mixture. Just imagine the sugar solution or a transparent solution in which sugar particles are not visible to your naked eyes. In the case of sugar solution, the sugar particles in water are not visible to your naked eyes, because in the case of a sugar solution, the size of the sugar particles in water will be less than 1 nanometer. In the case of sugar solution, the size of the sugar particles in water will be less than 1 nanometer, or you can say it will be less than 10 to the power of minus 9 meters. It's that 1 nanometer is nothing but 10 to the power of minus 9 meters. Because of that, sugar particles are not visible to our naked eyes, and the solution is highly transparent. And of course, such type of homogeneous mixtures in which the size of the particles will be less than 1 nanometer, they are called as true solutions. Or you can say crystalloids. Or you can say they are the crystalloids. Okay, now that is, true solutions are homogeneous mixtures in which the size of the particles will be less than 1 nanometer. They are also known as crystalloids. And as far as heterogeneous mixtures are concerned, I'll give one example, that is mixture of sand and water. Just imagine that mixture of sand and water, or the heterogeneous mixture. Here the sand particles are not uniformly distributed throughout water. That's why it is a heterogeneous mixture. And in the case of sand in water, in this mixture, sand particles are clearly visible to your naked eyes, is it not? Because in the case of mixture like sand in water, the size of the sand particles in water will be greater than 1000 nanometer. In the case of the mixture of sand and water, the size of the sand particles will be greater than 1000 nanometer in water. Because of that, the sand particles are clearly visible to your naked eyes. And of course, such type of heterogeneous mixtures in which size of the particles will be greater than 1000 nanometer, they are called as suspensions. So suspensions are, heterogeneous mixtures in which size of the particles will be greater than 1000 nanometer. Like that, we have different types of mixtures. One it will be, that is true solutions. Another it will be, yes, it is the suspensions. Now, in between these two extremes, we come across certain heterogeneous mixtures where the size of the particles will be in between 1 nanometer to, yes, it is 1000 nanometer. Okay, now? In between these two extremes, we come across certain heterogeneous mixtures in which size of the particles will be in between 1 nanometer to 1000 nanometer. Such type of heterogeneous mixtures are called as colloids. And of course, the credit of introducing the concept of colloids goes to Thomas Graham. The credit of introducing concepts of colloids goes to Thomas Graham. Okay, now he used the term colloids. The meaning of the term colloids is, yes, it is glue-like substances. Look at that. This colloids is from Latin literature. In Latin literature, that is colla means glue-like. That's why those substances we call them as colloids there. And as far as colloids are concerned, okay, now these are the heterogeneous systems in which that one substance is dispersed as fine particle having a size in between 1 nanometer to 1000 nanometer in another substance, and that heterogeneous mixture is called as colloids. Colloids are heterogeneous mixtures in which one substance is dispersed as fine particles having a diameter in between 1 nanometer to 1000 nanometer in another substance, and that is what we call it as colloid there. And of course, as far as the classification of yes, it is mixtures into true solutions, suspensions and colloids will be completely based on size of the particles in one particular medium. In the case of true solutions, size of the particles will be less than 1 nanometer in one particular medium. Whereas in the case of suspensions, size of the particles will be greater than 1000 nanometer in one particular medium. But in the case of colloids, the size of the particles will be maintained in between 1 nanometer to 1000 nanometer in one particular medium. And that's why, the properties of colloids will be in between those of true solutions and suspensions. Because of that particle size, the properties of colloids will be in between those of true solutions and suspensions. So because of that, now at this moment, I can define colloids as heterogeneous mixtures in which finely divided particles of one substance having a diameter 1 nanometer to 1000 nanometer is dispersed in another substance. So that is what we call it as colloids there. And of course, I said sugar solution is an example for true solutions. And of course, sand in water is an example for suspension. Now, I'll give one example, that is what we call it as starch solution. A starch solution is an example for, yes, it is colloids there. In the case of starch solution, the particles of starch will be dispersed in water medium. And this is heterogeneous mixture. Starch solution is a heterogeneous mixture in which size of the starch particles will be in between 1 nanometer to 1000 nanometer. Means in the case of colloids, size of the particles will be greater than 1 nanometer and it will be less than 1000 nanometer. And that's why, what I can say at this moment, any substance can be brought into colloidal state just by maintaining particle size in between 1 nanometer to 1000 nanometer in one particular medium. And that is what we call it as colloidal system or colloids, or you can say colloidal solution. So this is what we call it as colloids there. And of course, as far as the size of the particles is concerned, it will be 1 nanometer to, yes, it is 1000 nanometer, is it not? Yes. Just observe, it can be rewritten as 1 nanometer to, yes, it is 10 to the power of 3 into 10 to the power of 9 meters. This is 1000 can be written as 10 to the power of 3 into nano can be written as 10 to the power of minus 9 meters. And you can say this is 1 nanometer to 10 to the power of minus 6 meters. Or you can say 10 to the power of minus 6 meter can be replaced by 1 micrometer. That is, size of the particles will be in between 1 nanometer to, yes, it is 1 micrometer. So this is what we call it as size of the colloidal particles. Now that means it will be less, it will be greater than 1 nanometer, and you can say that less than 1 micrometer. And here the size of the particles will be expressed in terms of, yes, it is diameter there. Whatever the values that I am giving, that is, they are the diameters of the particles. Here the size of the particles will be expressed as diameter of the particle. Okay, now that is what we call it as, yes, it is the meaning of colloids. No doubt we considered colloids as, yes, it is heterogeneous mixtures, is it not? We considered colloids as heterogeneous mixtures. This heterogeneous mixture is characterized by two phases. Means colloidal solution is characterized by two components, or you can say two phases. One, it will be disperser phase. One, it will be disperser phase. This is one of the components present in colloidal solution. And second, it will be dispersion medium. Second, it will be dispersion medium. These are the two important components which constitute colloidal system. As far as disperser phase is concerned, disperser phase is a discontinuous phase which will be distributed in one particular medium in the form of colloidal particles. So that is what we call it as disperser phase. If I take starch solution, starch is a disperser phase, water is a dispersion medium. And as far as dispersion medium is concerned, it's a continuous phase. Dispersion medium is a continuous phase in which disperser phase is distributed in the form of colloidal particles. Or you can say in general, as far as disperser phase is concerned, it is a solute part of the colloidal solution, and dispersion medium is a solvent part of the colloidal solution. ಈಗ ಸೊಲ್ಯೂಷನ್ಸ್ ಅಲ್ಲಿ ಸಲ್ಯೂಟ್ ಸಾಲ್ವೆಂಟ್ ಅಂತ ಹೇಳ್ಬಿಟ್ಟು ನಮ್ಗೆ ಏನು ಎರಡು ಕಾಂಪೊನೆಂಟ್ಸ್ ಇದೆಯಲ್ಲ, ಅದೇ ತರ colloidal system ಅಲ್ಲಿ disperser phase that acts as a solute part of the colloidal solution. Dispersion medium is a solvent part of the colloidal solution. Or you can say disperser phase is present in smaller amounts and dispersion medium is present in larger amounts. And that is what we call it as disperser phase and dispersion medium. Now at this moment, we'll go to the next topic, that is classification of colloids. And the classification of colloids, that is, there are three bases for the classification of colloids. That is, classification of colloids will be based on three important aspects. One, it will be, yes, it is based on physical states of, yes, it is disperser phase and dispersion medium. This is one basis for the classification of, yes, it is colloids. We have three bases for the classification of colloids. One, it will be based on the physical states of disperser phase and dispersion medium. Second basis is based on the nature of interaction between disperser phase and dispersion medium. Third will be based on type of disperser phase particles in colloidal system. Third, it will be based on type of disperser phase particles in colloidal system. These are the three bases that I can make use of in order to bring about classification of colloids. We'll see one by one. First of all, it will be based on physical states of disperser phase and dispersion medium. For that purpose, you just have 4 columns. In the first column, it will be, yes, it is disperser phase. This is the first column, yes. Second column, it will be dispersion medium, yes. Second column, it will be dispersion medium, this second column. Third column, it will be, yes, it is type of colloid, yes. This is type of colloid, this is the third column, yes. And fourth, it will be examples for the different types of colloids. This is what we call it as the classification of colloids. No, just have 4 columns. Okay, now we'll see one by one. Okay, now first it will be the first type. It will be, yes, it is in the first type, solid will be disperser phase, and solid is yes, it is dispersion medium. Okay, now, and if the colloidal system is formed by solid disperser phase and solid dispersion medium, that type of colloid will be, yes, it is solid sol, we call it as. The type of colloid will be solid sol. Example for that, it will be colored glasses. That is, the second example will be gemstones like ruby stone and of course emerald stone. These are the examples for, yes, it is solid in solid type colloidal system, or you can say that solid sol. Look at this. In the case of colored particles, in the colored glass, solid colored particles will be dispersed in solid glass. In the case of colored glass, solid colored particles will be dispersed in a solid glass medium, is it not? That's why it is example for solid sol. In the case of ruby stone, the color of the ruby stones is because of presence of Cr3 plus ions in alumina. The color of the ruby stone is because of presence of Cr3 plus ions in Al2O3. Here, these colored Cr3 plus ions are acting like disperser phase. Al2O3 will be acting like, yes, it is dispersion medium. That's why it is an example for solid sol. Look at this emerald stone. Emerald stone is characterized by, once again, Cr3 plus ions. The colored Cr3 plus ions are dispersed in, yes, it is beryl. The colored Cr3 plus ions are dispersed in beryl. Beryl is, yes, it is silicate of aluminium and beryllium. It's a silicate of aluminium and beryllium, and in which, colored Cr3 plus ions are dispersed. Because of that, it's an example for, yes, it is solid sol. Okay, na? So this is what we call it as example for solid sols. Now at this moment, we'll go to the second type, that is dispersal phase is a solid and dispersion medium will be liquid. A colloidal system formed by dispersing solid in liquid medium, and it will be simply sol. As far as examples are concerned, we have a paint. A colored dye will be dispersed in a liquid medium, or you can say ink is an example for, yes, it is sol. Colored ink particles will be dispersed in, yes, it is water there, and third it will be cell fluids. Okay, now cell fluids are characterized by solid protein particles dispersed in water, or you can say solid nucleic acid particles dispersed in water. That's why it is an example for sol. Or you can say we go for gold sol. Yes, it's an example for, yes, it is sol there, where solid gold particles are dispersed in water. Or you can say starch solution. It's also an example for, yes, it is sol there. Okay, now here in starch solution, solid starch particles are dispersed in liquid water. These are all the examples for sols there. Okay, now, or you can say sulfide salts, metal sulfide salts, or the silver iodide salts, silver sol, gold sol. They are all examples for, yes, it is sols there. And as far as sol is concerned, sols will be of different types: alcosols and aquasols. If the dispersion medium is alcohol, and that type of sol is called as alcosol. If the dispersion medium is water, such type of sols are called as aquasols. That means sols can be of, yes, it is aquasols and alcosols. Okay, na? So that is second type. Third type it will be, yes, it is solid in, yes, it is gas type. Yes, solid in gas type. Okay, na? And this type of, yes, it is colloidal system is called as solid aerosol. It will be solid aerosol. This is a type of colloidal system. If dispersive phase is a solid, dispersion medium is a gas. And as far as examples is concerned, I can give example, that is dust, or you can say smoke. That is an example for, yes, it is the solid aerosol. Okay, now here in the case of dust, that colloidal solid mud particles will be dispersed in gaseous air. And here in the case of smoke, that is the carbon particles, solid carbon particles are dispersed in air. That is what we call it as smoke here. These are the examples for solid aerosol. And of course, fourth type it will be, look at this, yes, it is liquid in solid type. Yes, this is liquid in solid type. Liquid is, dispersive phase is a liquid, dispersion medium is a solid, and the type of colloid will be, yes, it is gel, we call it as. The liquid particles are dispersed in solid, resulting colloid will be gel. Examples for that, we have gel is, or you can say, you can give butter as an example for, yes, it is gel. In the case of butter, liquid water particles will be dispersed in solid fat. Or you can say, one more example, it will be cheese. Is it not? This is also an example for gel. So this is what we call it as one more type. And of course, the sixth type it will be liquid in liquid type. Your dispersive phase will be, yes, it is liquid. dispersion medium is also liquid, and the type of colloid will be emulsion. Or the type of colloid will be emulsion. Example for that, that is milk and of course hair creams. Milk and hair creams are the examples for it is emulsions. Here, in the case of milk, liquid fat particles are dispersed in water in presence of certain proteins. That is what we call it as emulsions. Liquid milk is an emulsion. Okay, now this is what we call it as emulsions. And the sixth type. It will be liquid in gas type. Yes, liquid in gas type. Dispersed phase is a liquid, dispersion medium is a gas, and it will be liquid aerosol. The type of the colloid will be liquid aerosol. This is liquid aerosol, a type of colloid where liquid is a dispersed phase, gas is a dispersion medium. Example for that, it will be mist, where water particles are dispersed in air, or you can say fog. Certain liquid molecules will be dispersed in air, or you can say cloud. Cloud is an example for liquid aerosol, where that is condensed water molecules will be dispersed in air. Apart from that, insecticide spray. Insecticide spray is an example for liquid aerosol. Insecticides are generally liquids. Here, when insecticide is spread, liquid insecticide particles will be spread in air. That constitutes liquid aerosol. And of course, as far as the seventh one is concerned, it will be gas in solid type. Seventh, it will be gas in solid type. This is one more type of colloidal system. And of course, it will be solid foam, we call it as. The type of colloid will be solid foam. Your gas is a dispersive phase, solid is a dispersion medium. Examples for that, it will be foam rubber. Foam rubber is an example for, it is a solid foam. Just imagine the rubber foam, the foam rubber that we use for manufacturing. It is sofas. That is foam rubber, in which the gaseous air will be dispersed in solid material. This is what we call it as foam rubber. Apart from that, this is cork is an example for, it is the solid foam, or you can say pumice stone. Pumice stone is nothing but it's a porous silicate in which gaseous air will be dispersed, and that is what we call it as pumice stone. Or you can say bread, or you can say cake is an example for, it is solid foam. In bread, the gaseous carbon dioxide or air particles will be dispersed in a solid phase. So this is what we call it as bread, or you can say cake. Or you can also give example, that is sponge as an example for solid foam. Yes. Apart from that, we have one more kind of colloidal system, that is here gas is a dispersive phase, liquid is a dispersion medium. Yes. Here gas is a dispersive phase, liquid is a dispersion medium. Gas and liquid type colloidal system, and it will be called as, it is foam, or you can say liquid foam. Okay, now, and as far as example for the liquid foam is concerned, froth is an example for, it is liquid foam, or you can say soap lather is an example for, it is liquid foam, or you can say whipped cream is an example for, it is the foam there. Okay, now, liquid foam. Okay, now, so these are the 8 types of colloidal system that we can constitute based on the physical states of dispersive phase and dispersion medium. And of course, the gas and gas type colloidal system is not possible, because mixture of any two gases is always homogeneous, but colloidal system is always heterogeneous. Because of that, the gas and gas type colloidal system not possible. If you take a mixture of any two gases, in which the size of the particles will be always less than 1 nanometer. Because of that, gaseous mixtures do not constitute what we call it as colloidal system. So this is what we call it as one way of classifying colloids based on the physical states of dispersive phase and dispersion medium. Among the types available, and that is most common colloidal systems will be salts, gels and emulsions. Among the types of colloids available, most common colloidal systems will be salts, gels and emulsions. But In this chapter, we are going to study something about, yes, it is salts and emulsions. Now, as I said earlier, if the dispersion medium is alcohol, the type of salts will be alcosols. If the dispersion medium is water, types of salts will be aquasols. Like that, that colloidal systems can be classified. Okay, now this is one way of classifying colloidal systems based on the physical state of dispersive phase and dispersion medium. We'll have this. Okay, now we'll see the next topic, that is classification based on interaction between dispersive phase and dispersion medium. We'll see that. Yes. So let us see one more type of classification based on the nature of interaction between dispersive phase and dispersion medium. Yes. And as far as the colloidal systems are concerned, what we said, it is a heterogeneous mixture. It's a heterogeneous mixture of dispersive phase and dispersion medium. And there is some sort of interactions, some sort of force of attractions between dispersive phase and dispersion medium. Based on the nature of interaction between dispersive phase and dispersion medium, I can classify colloids into two types. One, it will be lyophilic colloids, or I can say they are also known as intrinsic colloids. They are also known as intrinsic colloids. This is one classification, lyophilic colloids. Second, it will be lyophobic colloids. Second, it will be lyophobic colloids, and they are also known as extrinsic colloids. So this is one more classification of colloids based on the nature of interaction between dispersive phase and dispersion medium. Look at this, the term lyophilic. The meaning of the term itself says these are the colloids which are said to be solvent loving. Philic means affinity. Solvent loving colloids. Or you can say they are solvent attracting colloids. They are solvent attracting colloids or solvent loving colloids. Lyophobic. In this case, that is these colloids are, that is solvent repelling colloids, or you can say solvent hating colloids. Lyophobic, lyophobia, that means they hate solvents. Solvent hating or solvent repelling colloids. This is the meaning of the terms lyophilic and lyophobic. So let me see, what are these lyophilic colloids? Lyophilic colloids are the colloids in which dispersive phase particles have strong affinity for dispersion medium, and they are called as lyophilic colloids. The colloids in which dispersive phase particles have strong affinity for dispersion medium, and such type of colloids are called as lyophilic colloids. As far as examples for the lyophilic colloids are concerned, it will be examples, it will be gelatin, solution of glue, right? Starch solution, yes. Or you can say protein solutions, right, in water. Or you can say egg albumin. Egg albumin is one more example for lyophilic colloid. Or you can say that is polymer solutions in organic solvents. Polymer solutions in organic solvents, right? This is what we call it as one more example. That is gelatin, solution of glue, solution of gum, starch solution, protein solution, egg albumin, polymer solutions in organic solvents. These are all the examples for, yes, it is lyophilic colloids. In the case of lyophilic colloids, there is a strong interaction between dispersive phase and dispersion medium. That means there is a strong force of attraction between dispersive phase and dispersion medium. Because of that, in the case of lyophilic colloids, dispersive phase particles are extensively hydrated. That means the dispersive phase particles are surrounded by large number of dispersion medium molecules because of the strong interaction between dispersive phase and dispersion medium. For the same reason, these lyophilic colloids are relatively more stable. These lyophilic colloids are relatively more stable. At the same time, and because of that strong interaction between dispersive phase and dispersion medium, these lyophilic colloids can be easily prepared just by mixing dispersive phase and dispersion medium. At the same time, as far as lyophilic colloids are concerned, they cannot be easily precipitated. They cannot be easily coagulated. And that is one more important property as far as the lyophilic colloids are concerned. And all these properties are because of the strong interaction between dispersive phase and dispersion medium. And of course, these lyophilic colloids are called as reversible colloids. These lyophilic colloids are called as reversible colloids because if the dispersive phase is separated from dispersion medium, say for example by evaporation, that dispersive phase separated can again brought back into the colloidal solution just by remixing it with dispersion medium. That is, as far as lyophilic colloids are concerned, they can be called as reversible colloids because if the dispersive phase is separate from dispersion medium and that separated dispersive phase can again brought back into the colloidal solution just by remixing it with dispersion medium. That's why they are called as that is reversible colloids. For example, you take starch solution. If I heat that starch solution, all the water present in the starch solution will be evaporated. You will left with dispersive phase, that is starch powder. And that starch powder left, if it is remixed with water, you are going to get the colloidal starch solution again. Because of that, that is these lyophilic colloids are called as reversible colloids. And of course, as far as lyophobic colloids are concerned, these are the colloids in which dispersive phase particles have no affinity or little affinity for dispersion medium. Such type of colloids are called as lyophobic colloids. That is, lyophobic colloids they are the colloids in which the dispersive phase particles have no affinity or little affinity for dispersion medium. And such type of colloids are called as lyophobic colloids. And that means there is a weak force of attractions between dispersion medium and dispersive phase particles. And because of that weak interaction between dispersive phase and dispersion medium, lyophobic colloids are characterized by certain properties. The properties are, that is in the case of lyophobic colloids, the dispersive phase particles are not extensively hydrated or solvated. And these lyophobic colloids are relatively less stable. And these lyophobic colloids cannot be easily prepared. We need some special methods for the preparation of lyophobic colloids. At the same time, these lyophobic colloids can be easily precipitated. That is, in the case of lyophobic colloids, the dispersive phase particles can be easily precipitated just by agitation and by heating. Because there is a weak interaction between dispersion medium and dispersive phase particles. And of course, at the same time, lyophobic colloids are called as irreversible colloids because if the dispersive phase is separated from dispersion medium, that dispersive phase cannot be brought back into the colloidal solution by remixing it with dispersion medium. That is, the separated dispersive phase particles cannot be brought back into the colloidal solution just by remixing it with dispersion medium. Because in order to prepare these lyophobic colloids, we need some special methods, and that is what we call it as lyophobic colloids. As far as examples for the lyophobic colloids are concerned, we have gold sol. We have what we call it as silver sol. We have aluminum hydroxide sol. We have ferric hydroxide sol, or I can say silver iodide sol. Metal sulfide sols. These are the some examples for lyophobic colloids, or you can say extensive colloids. Now at this moment, let me differentiate lyophilic colloids and lyophobic colloids in brief. And that is very important discussion as far as your annual examination is concerned. You can expect 3 mark question. What are the differences between lyophilic colloids and lyophobic colloids? We'll see now the differences between lyophilic colloids and lyophobic colloids. Yes. So let us see the one more important discussion, that is differences between lyophilic colloids and lyophobic colloids. Let us see one by one. First it is, that is, dispersive phase has strong affinity for dispersion medium. This is one property of lyophilic colloids. Your dispersive phase has no or little affinity for, yes, it is dispersion medium. This is one difference. Second, that is lyophilic colloids are reversible. Lyophilic colloids are reversible. Lyophobic colloids are irreversible. That we discussed already. Yes. That is, lyophobic colloids are irreversible, right? Third, it will be dispersive phase particles are extensively solvated or hydrated. Yes. Dispersive phase particles are extensively solvated. Here, dispersive phase particles are not extensively, dispersive phase particles are not extensively solvated. This is one more difference. Fourth difference, lyophilic colloids are more stable. Lyophilic colloids are more stable, whereas lyophobic colloids are less stable. Yes, this is. And the fifth one is, as far as lyophilic colloids are concerned, that is, can be easily prepared. Can be easily prepared just by mixing dispersive phase and dispersion medium. Yes, it is. Cannot be easily prepared. Yes, cannot be easily prepared. They need some special methods for their preparation. Yes, cannot be easily prepared. Sixth one is cannot be easily precipitated. Cannot be easily precipitated due to the strong interaction between dispersive phase and dispersion medium. Can be easily precipitated. That is, you can make dispersive phase particles to undergo settling easily, but here dispersive phase particles cannot be easily settled. Easily. That is what we call it as sixth difference. Seventh difference is viscosity of yes, it is lyophilic colloids will be greater than the viscosity of dispersion medium. The viscosity of lyophilic colloids will be greater than viscosity of dispersion medium. Here, the viscosity of lyophobic colloids will be almost similar to the viscosity of dispersion medium, because there is a strong interaction between dispersive phase and dispersion medium. Thereby, the resistance offered by the lyophilic colloids for the flow of objects through it is very, very high. That's why viscosity of lyophilic colloids will be greater than the corresponding dispersion medium. Your viscosity of lyophobic colloids will be almost similar to the viscosity of dispersion medium. And as far as eighth difference is concerned, surface tension of lyophilic colloids will be less than that of the dispersion medium. Here, the surface tension of yes, it is lyophobic colloids will be almost similar to that of dispersion medium. Once again, reason is there is a weak interaction between dispersive phase and dispersion medium. So this is what we call it as the differences between, yes, it is lyophobic and lyophilic colloids. Yes, okay na? At least 3-4 differences correct like you ನೆನಪಿಟ್ಕೊಂಡ್ರೆ ಸಾಕು, you can easily get 3 marks. Okay na? So this is what we call it as differences between lyophilic colloids and lyophobic colloids. Yes. Let us see, that is one more classification of colloids based on the type of dispersive phase particles. Based on the type of dispersive phase particles in dispersion medium, colloids can be classified into, look at this, multimolecular colloids. Second, it will be macromolecular colloids. Of course, third, it will be associated colloids, or I can say micelles. So this is what we call it as 3 types of the colloidal systems: multimolecular colloids, macromolecular colloids, and associated colloids. So what are these multimolecular colloids? Look at the term itself says multimolecular colloids. Many molecules of substances will undergo aggregation to form colloidal particle here. multimolecular collides. Here the colloidal particle is formed by aggregation of large number of simple molecules or atoms. So multimolecular collides are the collides formed by the aggregation of large number of small atoms or molecules having a size less than 1 nanometer. Okay, na? That is generally, in the case of multimolecular collides, the size of the molecules will be less than 1 nanometer. When such type of small molecules undergo aggregation under suitable conditions, you are going to get a big colloidal particle having a size in between 1 nanometer to 1000 nanometer. And such type of the collides formed by the aggregation of large number of small atoms or molecules having a size less than 1 nanometer, they are called as multimolecular collides. For example, examples for the multimolecular collides will be sulfur sol and of course gold sol. These are the best examples for multimolecular collides. In the case of sulfur sol, colloidal sulfur particles are produced by the aggregation of large number of S8 molecules. And of course, as far as gold sol is concerned, it is produced by the aggregation of large number of gold atoms here. That is what we call it as gold sol. Like that, the colloids formed by the aggregation of large number of small atoms or molecules having a size less than 1 nanometer, they are called as multimolecular collides. Okay, na? Yes, that is multimolecular collides. Here, the particle size will be, yes, it is very, very small. Now look at this, particle size will be very, very small. The particle size will be less than 1 nanometer. When such type of small atoms or molecules undergo aggregation, you are going to get big particle having a size in between 1 nanometer to 1000 nanometer. So they are called as, yes, it is multimolecular collides. Look at this, yes, it is macromolecular collides. The term itself says you that macromolecular. That is, these are the collides formed by the big molecules. Macromolecular collides are the colloidal systems which will be formed by those macromolecules which are big enough to form colloidal solution in a particular dispersion medium. So for example, here size of the molecules itself lying between 1 nanometer to 1000 nanometer. Illi, the macromolecular collides alli molecular size 1 nanometer to 1000 nanometer madhye irtade. Hagagi, if such type of macromolecules are dispersed in a suitable medium, you are going to get colloidal system. So for example, generally macromolecular collides will be formed by, yes, it is the polymer solutions. They are formed by polymers. For example, that is starch solution is an example for, yes, it is macromolecular collides. Or you can say, yes, it is solution of cellulose. Solution of cellulose is an example for macromolecular collide. Protein solutions are the examples for, yes, it is macromolecular collides. All these, starch solution, cellulose solution and protein solutions, they are naturally occurring macromolecular collides. They are all naturally occurring macromolecular collides. Apart from that, solutions of polythene, polystyrene, solutions of polythene, polystyrene. Polythene is a polymer, polystyrene is also a polymer. Yes, nylon, or synthetic rubber. The solutions of, yes, it is polymer, the solutions of polythene, polystyrene, nylon, synthetic rubber, etc. They are all examples for macromolecular collides, or you can say they are examples for man-made macromolecular collides or synthetic macromolecular collides. Here it is, in the case of macromolecular collides, just observe the molecular size itself is very, very large. Size of the molecule itself is very, very large, and the size of the molecule will be in between 1 nanometer to 1000 nanometer. Therefore, if such type of big molecules are dispersed in a particular medium, you are going to get macromolecular collides. Here, in the case of multimolecular collides, look at this. The particle size will be very, very small. It will be less than 1 nanometer. Because of that, large number of such type of small atoms or molecules undergo aggregation, and these particles are held together by some van der Waals force of attraction, and to form a big particle having a size in between 1 nanometer to 1000 nanometer, and that is what we call it as multimolecular collides. In the case of colloidal sulfur particle, sulfur molecules are held together by van der Waals force of attractions. In the case of gold sol, gold atoms are held together by van der Waals force of attraction. So this is what we call it as the multimolecular collides and macromolecular collides. Now at this moment, we'll go to the one more type of, yes, it is colloidal system. It will be associated colloids, or you can say micelles. It will be associated colloid, or you can say micelles. So see that, yes, associated colloids, or you can say they are also known as micelles. Look at this, and once again, look at the term associated colloids here, because of the association of smaller molecules under suitable conditions. And as far as associated colloids are concerned, associated colloids are the colloids which behave as strong electrolytes at lower concentrations but exhibiting properties of colloids at higher concentrations due to the aggregation of particles at higher concentrations. Such type of colloidal systems are called as associated colloids, or you can say micelles. And these aggregated particles exhibiting colloidal behavior are called as micelles. These aggregated particles which will be exhibiting properties of colloids at higher concentration, they are called as micelles. Okay, na? That is, in the case of associated colloids, at lower concentration, the substances, they behave like, yes, it is true solutions, where the particle size will be less than 1 nanometer. And at higher concentration, there is aggregation of smaller particles takes place that results in the formation of a bigger particle having a size in between 1 nanometer to 1000 nanometer. Okay, na? And that results in the formation of colloidal system. And those aggregated particles exhibiting colloidal behavior, they are called as micelles. Because of that, as far as associated colloids are concerned, these are the colloids which behave as strong electrolytes, or you can say true solutions at lower concentration but exhibiting properties of colloids at higher concentration. Due to the aggregation of particles, they are called as associated colloids. And examples for the associated colloids will be solutions of soaps and detergents. Solutions of soaps and detergents, they are the examples for associated colloids. As far as soap solution is concerned, soap solutions behave like strong electrolytes at lower concentration, but at higher concentration, there is aggregation of soap molecules takes place that results in the formation of associated colloids. That's why soaps are the examples for, soap solution is an example for associated colloids. So also the solutions of detergents will be examples for associated colloids or micelles. And of course, as far as aggregation of particles is concerned, that aggregation of particles takes place only above a particular concentration known as critical micelle concentration. Critical micelle concentration is a concentration of colloidal solution above which formation of micelle takes place, and that is called as critical micelle concentration, or it can be abbreviated as CMC. And as far as soap solutions and detergents are concerned, CMC for soap solutions will be 10 to the power minus 4 moles per liter to 10 to the power minus 3 moles per liter. This is critical micelle concentration for soap solutions and detergents. And means this is a minimum concentration above which micellar formation takes place. At the same time, aggregation of particles takes place only above one particular temperature known as Kraft temperature. That is Kraft temperature. That is critical micellar concentration and Kraft temperatures. They are the properties of that is associated colloids. Different associated colloids have different CMC values and different Kraft temperatures. Different associated colloids have different CMC values and different, yes, it is Kraft temperature. CMC for soap solution is 10 to the power of minus 4 mole per liter to the 10 to the power of minus 3 mole per liter. So this is what we call it as CMC for soap solutions. That is, what is CMC and this is a concentration of colloidal solution above which micelle formation takes place. That is called as critical micelle concentration. And Kraft temperature is a temperature above which micelle formation takes place. That is called as Kraft temperature. And of course, as far as your syllabus is concerned, we are supposed to discuss mechanism involved in the formation of micelles, or you can say at the same time we have one more discussion, that is the cleansing action of soaps. So let us see the next discussion under colloids. It will be mechanism of micelle formation. As far as micelles are concerned, micelles are formed by aggregation of a large number of molecules containing hydrophilic part as well as hydrophobic part. For example, the molecules of soaps and detergents will be characterized by hydrophilic part as well as hydrophobic part. The common composition of soaps will be, yes, it is sodium stearate. This is the composition of, yes, it is soaps. As you know that soaps are the sodium salts of long chain fatty acids, and soaps are generally represented by the formula RCOO minus, and of course this is the composition of soap. Okay, na? RCOO minus Na plus. This is sodium salt of long chain fatty acids. Example for the soap will be, yes, it is sodium stearate. The formula of sodium stearate will be C17H35. Yes, it is COONA. This is what we call it as formula of, yes, it is sodium stearate. This is the common composition of all soaps. Look at this particular sodium stearate molecule. When it is dissolved in water, it produces, yes, it is C17H35 COO minus plus Na plus ions, and this is what we call it as the negative ion. Stearate ion is a negative ion, and of course Na plus ions will remain in water. Look at this stearate ion. It is characterized by 17 carbon atoms, and of course another is COO minus. This stearate ion from soap molecule is characterized by non-polar tail, that is hydrophobic part. Look at this C17H35. Look at this. This is a chain of 17 carbon atoms, and this is chain of 17 carbon atom. This chain of 17 carbon atom will be, yes, it is non-polar tail. It is non-polar tail of the stearate ion, athwa non-polar tail of the soap molecule. And look at this COO minus, that constitutes polar head of the stearate ion, athwa polar head of the soap molecule. When such type of molecules containing non-polar part as well as polar part, if they undergo aggregation, that results in the formation of what we call it as micelles. The micelles are due to the aggregation of large number of molecules containing hydrophilic part as well as hydrophobic part. This non-polar tail is what we call it as hydrophobic part. That is, this part of the soap is insoluble in water, athwa this part of the soap has less affinity for water, whereas polar head of the soap has got much affinity for water. That's why it is called as hydrophilic part. This is hydrophilic part of the soap, and this will be hydrophobic part of the soap. And such type of molecules containing, yes, it is hydrophilic part as well as hydrophobic parts undergo aggregation to form a spherical shaped particle called as micelles. And of course, as far as the soap solution is concerned, if I consider soap solution at lower concentration, just observe, soap molecules will remain at the surface of the water. Okay, now at lower concentration, soap molecules will remain at the surface of water with their polar heads in the water, and non-polar tails will be away from the water. Look at this. The tails are, they are non-polar parts. They are hydrophobic. They don't have an affinity with water. That's why they are away from the water there. Whereas polar head, that is negatively charged polar head. Negatively charged polar head, that will be in the water, because it will be, polar head will be soluble in water. It is hydrophilic part. The red particle, red colored sphere, that is red colored sphere, that is hydrophilic part. It will remain in water, whereas hydrophobic part, that will be away from the surface of water. This is how the soap molecules will remain at the surface of, yes, it is water at lower concentration. That's why these soap molecules are called as surface active agents, we call them as, because as these soap molecules will remain at the surface of water, they are called as surface active agents. And of course, at critical micelle concentration, as the concentration of soap molecules in the water increases, that these soap molecules will be pulled into the bulk of the liquid, and that results in aggregation of soap molecules to form spherical shaped particle with their non-polar tails pointing towards the center of the, sphere, and polar heads of the soap molecules will be pointing outward on the surface of the spherical sphere. That results in the formation of, yes, it is spherical shaped, yes, it is a particle, and that is what we call it as micelle, or you can say that ionic micelle. This is how that micelle will be produced at critical micelle concentration. So this is the mechanism involved in the formation of, yes, it is the micelles. Okay, now, and of course same type of mechanism can be used in order to explain formation of micelles in the case of detergents. The examples for detergents will be sodium lauryl sulfate. Sodium lauryl sulfate is an example for detergent. The formula is, yes, it is CH3, right? And of course CH2 11 times, and of course SO4 minus, and of course Na plus. This is what we call it as sodium lauryl sulfate. Just observe, just like in the case of soap, this detergent is also characterized by non-polar hydrophobic part and polar, yes, it is hydrophilic part. Polar hydrophilic part will be constituted by, that is SO4 minus ions in detergents, and non-polar hydrophobic part will be constituted by the 12 carbon atoms in yes, it is hydrocarbon chain. So this is what we call it as yes, it is the formation of micelles. Okay, na? Mechanism involved in formation of micelles. Now at this moment, we'll go to the next topic, that is cleansing action of soap. Okay, na? How exactly soap is going to remove dirt from the surface of cloths. That is the next discussion. We'll see that. Yes. Now let us see that next discussion, that is cleansing action of soap. Before discussing this cleansing action of soap, let me introduce what exactly that soap is. As I said, soap is yes, it is a sodium salt of long chain fatty acids, and that soap is characterized by, yes, it is non-polar hydrophobic part. Hydrophobic part, that is water repelling part of the soap, and polar hydrophilic part, that is water attracting part of the soap. Or you can say this hydrophobic part, it is repelled by water, but it is attracted by oil or grease, because oil or grease are non-polar substances, and that's why oil or grease, they are attracting non-polar part of the soap, and this particular polar group is attracted by water, but it is repelled by oil or grease, because polar part is repelled by, yes, it is non-polar substances like oil or grease. Look at this. As far as cleansing action of soap is concerned, cleansing action of soap is due to the formation of micelles by soap molecules around the, yes, it is oil droplet containing dirt on the surface of cloth. And of course, you just imagine a dirty cloth with a dirt on its surface in presence of oil or grease. That means dirt will be stick to the surface of cloth in presence of oil or grease. Oil or grease are non-polar substances. When such type of dirty cloths are dipped in soap solution, that soap molecules will be attached to the surface of oil droplet containing dirt with their non-polar tails in the oil droplet, and polar heads will be on the surface of oil droplet. So this is how soap molecules will be surrounding oil droplet containing, yes, it is dirt on the surface of cloth. And just observe, these polar heads of the soap molecules are strongly attracted by the water molecules above their surfaces, and because of that, oil droplet containing dirt will be removed from the surface of cloth into the water in the form of, yes, it is micelle, in which the soap molecules will be attached to the, yes, it is oil droplet with their tails pointing towards the center of oil droplet and polar heads above the surface of oil droplet. And of course, now at this moment, this micelle is strongly interacting with water due to the presence of negatively charged sheath on its surface. And because of that interaction with water molecule, this oil droplet will form stable emulsion with water. And this is how, dirt will be removed from the surface of cloth by forming stable emulsion of oil with water in presence of soap. So this is what we call it as mechanism involved in removal of dirt from the surface of cloth. And of course, as far as that is sheath of negative charges on the surface of micelle is concerned, this sheath of negative charges on the surface of oil droplet prevents aggregation of oil droplet, thereby that supports formation of stable emulsion of oil droplet with water. So that is at this moment what I can conclude, that dirt will be removed from the surface of, yes, it is cloth, but due to the formation of, yes, it is micelles by the soap molecules with oil droplet containing dirt. So this is what we call it as the mechanism involved in, yes, it is cleansing action of soap. That's all about cleansing action of soap. Okay, now in the next video we'll see the methods of preparation of colloids and properties of colloids. That we'll see in the next video. Okay, now thank you. Right.